Hello everyone, this is going to be Mass Autoencoders, or Scalable Vision Learners, paper explained in 5 minutes. Alright, so this paper is about self-supervised learning applied to images. So self-supervised learning is in contrast to supervised learning, where usually you need a piece of data and a respective label. But with self-supervised learning, you can take your data and then get some sort of label from the data. So you do not need explicit labels. And so this worked really well in NLP. And so the authors note that techniques like BERT and GPT can take a sentence like the and put a mask token. So this would be a mask token. And the model can predict what the mask token will be. So this is going to be quick. And so notice how this doesn't require any explicit labels, because you can do this many, many times. You can run this again where now this is the mask and so on. So there's no need for explicit labels here. You can train a model using the existing data without labels. But the authors note that information density is different between language and vision. So let's take, for example, this image of this bird here, this flamingo. If I mask out this section or this section, you can still tell it's a flamingo. And this is because data in images is much more redundant as compared to language, where information is packed into each word. And so the authors propose their approach, masked autoencoders. And so how they accomplish this task of self-supervised learning is they'll divide this image into a lot of patches. So they'll take this image of the flamingo, and each square here is a mask. And so they're going to mask it about 75%. Then they're going to take only the unmasked regions, and then they're going to arrange them as so, pass them through an encoder. So now these are going to be latent representations. Then they're going to append placeholders for the masked tokens. So this originally masked token is going to go back here. Then the entire thing is going to go through the decoder, and the decoder is going to predict pixels for where the masked tokens were. And so they note that their approach yields really good performance in downstream tasks, which is the goal of self-supervised learning, and is extremely scalable. So if you look at some of the results here, you can see that an image like this, and this isn't from the train set, this is from the validation set, an image like this, where it's heavily masked, these are all masks, it can very accurately predict new information that it hasn't seen, such as in here. And that's because through self-supervised learning, it's learned a good representation of its data set, which is, in this case, ImageNet. You can see when they test with different mask percentages, different scenarios happen. So at a lower percentage, you have more information, and so it generates these multiple of these mushrooms. But when you only have really these amounts of pixels, it's remarkable that it even knows it's a mushroom, but it generates one mushroom, which is a plausible scenario. Same here. So when all this information is masked, it just generates more of these tomatoes. And so they actually investigate the ideal masking ratio, and they find that it's about 75%. And so you may wonder, hey, this isn't a good image. Why don't they lower the masking percentage? And the answer is the goal isn't to make a good image. The goal is to make the network learn, to force the network to learn. So you want to give the network a hard enough task, a high enough masking ratio, so that it's learning. But then if it's too high, the model won't have enough information. So the task is too hard. So you want to kind of find that Goldilocks spot between too easy and too hard of a task. And another thing to note is these little squares. And how come the unmasked tokens kind of show up blurry here? And the reason is because the loss is only for the masked patches, not for the visible patches. So the model doesn't optimize these. All right. And then another thing is the decoder. So if you go back to the original image, the first figure, you can see that the decoder is really small. And this is for two reasons. First is they're trying to make a really scalable approach. So that means they're trying to optimize the number of parameters, and keeping the decoder small makes this more efficient. Another reason is because they want the encoder to learn, because in self-supervised learning, typically you're training an encoder with a decoder, but then what you end up doing is you end up getting rid of the decoder and then putting some sort of like either this linear or whatever, or a different decoder entirely, but you keep the encoder. So this is what you want to train. And so another interesting thing is they look at different ways of sampling. So this grid is a little too easy because even if, let's say, this token is masked, you can see this token, this token, this token, this token. So you have a pretty good idea of what that token is. Then they try this huge blocking strategy. And this blocking strategy is interesting because it's still used by other self-supervised learning approaches today. But the authors found that this random masking was just better for their use case. And it allowed more of the image to be masked, which made it more efficient because remember that the masked tokens don't get passed through the encoder, right? They're appended after the pass through the encoder. So getting rid of as many or masking as many tokens as possible makes the entire model much more efficient. Alrighty, that was masked autoencoders or scalable vision learners. Paper explained in 5 minutes. Thank you very much. And I'll see you in the next one.